We're obsessed with training neural networks, but what if there's a more powerful way to create? An approach where solutions aren't trained, but are born and evolved. Decades before today's AI, a field called genetic algorithms laid the groundwork for code that could literally rewrite itself. It's powered by the same principles of evolution that created us: digital DNA, mutation, and crossover. I spent my PhD on this in the 90s, and the core ideas, making use of scaled computation, are making a massive comeback to solve problems that LLMs alone can't. So this is a little bit of history really, from back in the mid-90s, when neural networks only kinda worked, and hidden Markov models and support vector machines were kind of on the horizon. There was still something which actually kind of worked. The genetic algorithms, genetic programming, actually was a technique which worked at the time. So my PhD, rather than doing the neural networks which was intended of me, became an investigation into these genetic algorithms and what we could do with them. So, back in the mid-90s, neural networks only kind of worked. They were very small and people hadn't fully understood how to make them train reliably. And up-and-coming things like hidden Markov models and support vector machines with a firm mathematical foundation were coming up quickly and essentially overtook the neural network field during the 2000s up to like 2010 with the ImageNet moment. However, back in the 90s, I decided instead of doing the neural networks that most of my lab was focused on, I would look into genetic algorithms and genetic programming, which actually worked at the time. Let's go through the basics of genetic algorithms. Here, instead of looking at one single neural network and improving it via gradient steps towards the perfect neural network, what we do is we look at a whole population of different individuals, where each individual is perhaps a neural network. We're going to represent these individuals by strings of bits, and the population could be hundreds of these. For each one, we're going to be able to compute a fitness measure. So basically, this is how well that individual performs against our task. Now, importantly, we're not going to need any differentiation to do that, so we're not going to take gradient steps. We're just going to look at how fit each individual is, and then play a game of survival of the fittest. We're going to select the best individuals we can, or a good selection of individuals, and then we're going to do two operations, one called mutation, another crossover. This will allow us to generate new individuals, new bit strings, and then we can evaluate the fitness on them and continue this whole process. We will also throw out the bad ones, so basically there's going to be a whole survival of the fittest thing going on. So let's see this in a diagram. In the top left, let's think of this as the list of all the individuals, and we're then going to pick out two pairs actually here. You can see in the top we've got this pair, which are these individual bit strings, and there's a second pair here. And we're actually going to choose some crossover points with these dotted lines, and it's at this point we're going to switch around between the two individuals. So in the first row here we've got single point crossover, where you can see this bit string has been cut and then the two individuals flipped. And in the second one we've got a 2-point crossover where a substring has been flipped over between the two. We then take these flipped things down in the bottom right corner. We may mutate some of the bits in here, just flip them at random. And then from those we have 4 new individuals, and we're going to evaluate the fitness of those and then insert them back into the table of individuals, or back into the population. Basically, this is the cycle which is going to go round, essentially creating new individuals and destroying the less fit ones. So even back in the 90s, when it was difficult to train a very large neural network, we could still do decent experiments on these genetic processes. And the kind of upshot of this, it was kind of widely believed and observed that mutation, while it seems like from standard talk about mutations in individuals as being a driving force of evolution, actually crossover is the thing which powers global search. And so the crossover operator here is doing a lot of the work, whereas mutations are kind of hedging around the edges. It's interesting though that mutation is more similar to what we're doing with neural networks with gradient descent, except that with neural networks we know the essentially the perfect direction in which to head, whereas in mutation we're taking random directions. So it's maybe no surprise that mutation is definitely weaker than gradient descent. On the other hand, this crossover was actually found to be kind of the dominant improvement mechanism. So there are strong parallels with nature here, particularly compared with what neural networks might be doing compared to what the brain is doing. We find that mutations are clearly a thing, and we'd find that in nature as well. But noticing from nature, practically all species have two parents. There's a fundamental driving force which evolution has discovered over billions of years, and this is something which is not really captured in standard neural network training, but we do capture in these genetic algorithms. So one of the questions, even back then, is how does crossover work so well? And so there's going to be a bunch of hand waving here. There were various kind of theories and ideas which existed, but I would say they're not particularly convincing. On the other hand, the bottom line is that this crossover thing does work very well. It's just very difficult to explain why it works so well. So one way of thinking about crossover was in terms of exponential exploration. And here we're going to apply kind of a sampling idea. So suppose we have an individual which is 0, 1, 0 plus a whole lot of other bits, and its fitness is 5.7. Clearly, that tells us what the answer is for that individual, but thinking was that it also is an estimate of all of the individuals which are 0 something 0. It's also an estimate of something something 0. So this single fitness value can play the job of being an estimate at an exponential number of individuals, and using those results across a population you can actually derive interesting statistics. This may sound persuasive and it may have some element of truth. On the other hand, it does seem a bit suspicious that a single number can give rise to kind of exponential power. It doesn't sit right in some ways. Okay, so this is one idea. Another theory, a schema theory, put forward by John Holland in 1975, basically observed that if you took small substrings within the large individual bit string, those small substrings with above average performance and short lengths will be sampled exponentially many times. Basically, this is saying that if you've got useful ideas in your bit strings, the more useful ideas will get sampled more often, and this is what is driving evolution. This is also an interesting kind of way of looking at it, and it's kind of supported by evolutionary theory, as per this counterpoint. On the other hand, that same idea has too much generality to really observe what we're seeing. So another way of looking at this was the building block hypothesis, and this had similar ideas about the importance of these substrings. In particular, how do these substrings gain meaning? And here we point out that the crossover acts on segments of these strings, or segments of these individual bit strings, and so the segments become meaningful. And they become meaningful because of the crossover operator. So in some ways, if the crossover operator respects useful segments or can pick out useful segments, that is actually where these things could lever themselves up. So in that sense, what we really want to do is make sure that our bit string or our representation can be segmented in a suitable way. So this, I kind of like this a bit more, and we'll see why in a moment. So, inspired by genetic algorithms, I mainly studied genetic programming. Now this is where instead of fixed bit strings, we actually manipulate programs and use a program as the individual. So on the left-hand side, you can see like a familiar algebraic expression, and on the right is kind of a tree of operations. So this is slightly rearranged. We've got the root of b squared minus 4ac minus b, all divided by 2 times a. So the tree is equivalent to the algebraic expression, but it has some nice properties. In particular, this tree representation allows us to do a crossover operation between two individuals. So suppose we have the top 2 programs up here, and then we'll focus on these subtrees, which are highlighted. Now, The crossover operator simply switches over the subtrees between these two things, and the bottom is then the result of having done this, and these are the two new individuals. So this crossover operator appears to be madness. How can it be that these two programs survive having like subtrees exchange between them? What we find, though, is actually this process does work rather well. The whole genetic setup is very robust. And let's compare this to getting neural network derivatives just right, which admittedly frameworks do now, or reinforcement learning to work, which is super sensitive. The genetic stuff likes to work, and it will, essentially, even if you program it wrong, it will get it right. It's insane that these work so well. So the lesson of this genetic programming and crossover is that the behavior of the population is not the same as having the behavior of an individual 100 times. There's something else going on here. And so for this to work at all, what we need is the qualities that propagate through the population or through the generations lead to individuals which are more robust to having pieces switched out. And so this is kind of part of my PhD. We can look at the dead code within these trees. We can actually see there's kind of junk DNA being stored around so that these things become more robust. This is a super interesting parallel between nature and what we discover programmatically. So overall, genetic programming has continued to evolve. There's a huge biography of people using these things to create new solutions. One of the key people involved in the field, Koza, listed many results where genetic programming results were human competitive across all sorts of very diverse engineering fields. So one of the reasons I preferred the genetic programming line rather than genetic algorithms is that the genetic programming lent itself to essentially re-engineer the code to make it more amenable to the genetic process. Whereas in genetic algorithms, you kind of have to define how the bit string is translated into an individual. The genetic programs basically could refactor themselves. So this is similar to the argument between genotype versus phenotype in genetics. So here's a diagram stolen from examples.com. On the left-hand side, we've got the genotype. Basically, this is the DNA, or would be the fixed bit strings, or the tree representation. This is the actual thing which is being manipulated by the genetic operators. So the crossover and mutation occurs with the left-hand side representation. On the other hand, the actual individuals, when they behave in the real world or are a neural network or whatever, this is what the actual expression of this representation turns into. So, for instance, eye color is known to be just a few genes on the left-hand side and translates onto something on the right-hand side, which is very specific. On the other hand, there's probably stuff on the left-hand side which will be easy to mutate or easy to crossover, units on the left-hand side, which may have very indistinct effects on the right-hand side. And it may just be we don't understand what these things are really doing, but there's some benefit in having that as being mixed all across DNA, as opposed to just a single place where it can be affected. So DNA has, the whole evolution process has done something very subtle to make the genetic code on the left work as expressions, or when expressed in individuals. And so there'll be some things which are easy to fix, like eye color, and some things which are very difficult to fix just because the effects may be very broad. It may look very specific on the right hand side, but it might be distributed in a very weird fashion across DNA, just because you don't want single errors to affect everything on the right hand side. So there's something very interesting going on between the representation which you can affect and the actual individual on the other side, which is, in the case of DNA, you may have individual letters which contribute to proteins, which then get folded into a mechanism which builds a thing which eventually becomes the human, which behaves in a way. But that process is, it removes the actual actions we can take from the end result by quite a distance. And you might say, well, that's unfortunate. It would be better to be able to manipulate the thing on the right directly. But there's probably a reason, and evolution has been working at this for far longer than we have been working on neural networks or science in general. So it'd be unwise to suggest that this process is ridiculously bad just because we don't understand it. So let's move on to some of the basics of evolution here. Here's a quote from Darwin, which is saying that the preservation of favourable individual differences and variations and the destruction of those which are injurious I've called natural selection or survival of the fittest. Now this is the standard survival of the fittest quote, but to my taste and probably to his, this is essentially a circular definition. Basically it's saying which stuff which is favourable survives and stuff which isn't favourable dies off, but the definition of surviving and dying off is basically interlinked with favourable to such an extent that this is almost a circular definition. This is a definitional thing rather than an observation, as it were. So here is another quote from Darwin, which doesn't capture the imagination in quite the same way as survival of the fittest, but is probably more instructive for his theory and also the evolution methods we're looking at. Saying it's not the strongest of the species that survives, not the most intelligent that survives, it is the one that is most adaptable to change. Now this is very interesting, since it also speaks to, in particular when I was looking at genetic programming, how the role of survivability to these crossover operations works. You can also think about this in terms of what other higher level actions this would promote in order to avoid being destroyed. And so you can see this in terms of adaptability of the overall genetic process will also have these qualities. So this is why I think this is a much stronger statement about evolution. Okay, so to wrap up, these evolutionary ideas have been around for a very long time. We can still learn lessons from what Darwin originally observed. One interesting thing in today's parallel computation environment is these are embarrassingly parallel problems. If you want to scale across a population, we can run this on many GPUs at once and get the results back. We could even do it in a distributed fashion globally. So there's a lot to be liked about this if we can make it work for our problems. In terms of lessons learned, which are still valid today as they were in the 90s, we have a few things. Firstly, don't just do mutation. If essentially your process relies on having lots of individuals and then moving them all on a little bit towards hopefully better outcomes, this will work, but slowly. One of the key things to do is get this crossover working, and then once you have the mixing of two things, then you'll have a much more natural kind of evolution happening, one that was chosen by nature. And so this is where this kind of exponential power comes in, which is still not well understood. Another thing to think about is what is the DNA in our individuals. Now, it may just be a bit string, but that seems too limited. Now the programs also may be too limited a substrate. It may be you want a program which writes a program to do the behavior. The aim is to make something which can be evolvable. A final lesson from the 90s is to be very careful with what you ask to be optimized by these methods. These genetic processes are very opportunistic and will often find a way to undermine your reward or find a trick to cheat to get their evaluation scores up or their fitness. As we learnt from Jurassic Park, life finds a way. With that, thank you very much for joining me for this episode. We're going to have a few more in this series, gradually bringing us to the present day. And from there, I'll be able to talk about the kind of topics I discuss in the Machine Learning Singapore meetup, for instance, which are typically very topical. So this has been a bit of a history lesson, but it'll be worth it in the end. Cheers.